All right, let's jump right in. When you board a commercial flight, you probably notice the cabin crew, you fiddle with your seatbelt, and you maybe watch the safety video. But honestly, long before you even step onto that jet bridge, a massive, totally hidden network of safety concepts has already dictated every single parameter of your flight. In this explainer, we're going to decode the secret language of aviation. We're talking about an invisible, highly mathematical grid that ensures your heavy metal tube can safely launch into the sky and, just as importantly, stay safely on the ground if things go sideways.
Here's our flight plan for this explainer. We're going to cover the invisible air, airport secret codes, the runway ruler, the takeoff balancing act, and finally, catching runaway planes.
Part 1. The invisible air. Understanding atmosphere.
Okay, before our aircraft even turns on its engines or moves an inch, we have to look outside at the invisible forces acting on it. The air is our medium, right? And it's constantly changing. Now, density altitude. It's actually not about physical height at all. It's a brilliant analogy for how thick or thin the air literally feels to the airplane. You see, airplanes move through a fluid, and the density of that fluid totally changes how much lift the wings can generate and how much power the engines can crank out. When the temperature and altitude go up, the air density actually goes down. So, on a scorching hot summer day, a plane sitting on a runway right at sea level might actually feel like it's trying to take off from a mountain airport thousands of feet up in the air.
To break it down simply, true altitude tells you exactly where you are on a map, your literal physical distance above sea level. But density altitude, that tells the aircraft's engines and wings how well they're actually going to perform in the current weather. If the density altitude is high, your aircraft's performance is going to be low. It means you're going to need way more runway to get airborne, and your climb is going to be super sluggish. Pilots rely heavily on this critical calculation to know exactly what the plane is capable of on any given day.
Moving on to Part 2. Airport secret codes. Ensuring compatibility.
So, now we know how the air feels today. Let's figure out if our specific airplane is even allowed to taxi around this airport. Civil engineers actually condense massive, complex dimensions into a really simple code. The International Civil Aviation Organization, or ICAO, uses an aerodrome reference code just to match aircraft with airport facilities. It's a two-part code. The first element is a number, from 1 to 4, which represents the runway length. Basically, any commercial runway over 1,800 meters long gets a Category 4. The second element is a letter, from A to F, and this determines the maximum allowable wingspan. It is such an ingenious way to guarantee a plane physically fits into the space. To put that into perspective for you, an everyday Airbus A320, a total staple of domestic flights, easily fits into a 3C or 4C slot. That C just means its wingspan is somewhere between 24 and 36 meters. But take a giant double-decker Airbus A380, that beast demands a 4F rating. The F means its massive wing stretch between 65 and 80 meters. If an airport's taxiways and gates aren't rated for an F, that A380 simply isn't allowed to land there. No exceptions. It guarantees those wings won't go clipping buildings, light poles, or, other planes.
Part 3. The runway ruler. Declared distances.
All right, so the aircraft is compatible, the weather is factored in, and we are lining up on the pavement. But how much runway do we actually have to work with? These are called declared distances, translating a bunch of dense acronyms into the physical spaces available for the takeoff roll. Step 1 is TORA, or Takeoff Run Available. This is the actual physical pavement declared suitable for the airplane's tires to roll on while it accelerates. Step 2 is TOTA, or Takeoff Distance Available. This takes that TORA and adds any clearway, which is an airspace beyond the runway that's totally free of tall obstacles, used specifically for the initial climb. And Step 3 is ASDA, Accelerate Stop Distance Available. This takes the physical runway and adds any stopway, a stretch of pavement designed strictly for emergency braking, not for taking off. Now, it is absolutely crucial to understand this next part. The distance you have to take off might be completely different than the distance you have to land. You might look out at a strip of concrete and assume, hey, we can use all of that, right? Not exactly. Because of obstacles on the approach path, or construction, or what we call displaced thresholds, where the usable part of the runway starts further down the pavement than it physically looks, the official landing distance available, or LDA, might be significantly shorter than the TORA used for taking off. Pilots rely strictly on these official declared distances, not just a visual guess out the window.
Part 4. The Takeoff Balancing Act. Physics in Motion.
So, the pre-flight math is completely done. The engines are roaring, we're rolling down the TORA, and now the pilots are relying on some intense, invisible physics. This right here is the ultimate aviation balancing act. Imagine the aircraft speeding down the runway.
If an engine suddenly fails, the pilot faces a huge choice. Do I hit the brakes, or do I keep going and literally fly on one engine? A balanced field takeoff calculates the exact, perfect scenario where the distance required to smash the brakes and safely stop, using that ASDA we just talked about, perfectly equals the distance needed to just continue the takeoff and climb into the sky on the remaining engine.
And that leads us to V1. V1 is that exact split-second speed where this mathematical balance happens. It is literally the point of no return. If an engine fails even a split second before reaching V1 speed, the pilot must aggressively hit the brakes, use reverse thrust, and abort the takeoff, knowing for a fact they have exactly enough runway left to stop. But if an engine fails a fraction of a second after reaching V1, the pilot has to completely commit to flying. Trying to hit the brakes after V1 pretty much guarantees the plane will run right out of runway.
By achieving this perfect mathematical balance prior to every single flight, airlines are actually doing two big things. First off, they guarantee that no matter when an engine failure happens, there's a safe, pre-calculated way out. Second, it lets them maximize their efficiency. By perfectly matching the aircraft's weight to the balanced field length of that specific runway on that exact day, they can safely load the maximum amount of passengers, cargo, and fuel without ever risking a runway overrun. It's safety and economics working in total harmony.
Even with all of these incredible calculations, aviation always prepares for the absolute worst. So, what happens if a plane simply can't stop in time? What if there's an unforeseen mechanical failure? What if the brakes give out or the runway is unexpectedly super icy and an aborted takeoff goes way long? It's definitely a terrifying thought, but it leads us perfectly into our final, ultimate layer of safety.
Part 5. Catching Runaway Planes, RISA and EMAS.
Welcome to the very end of the runway, where civil engineering steps in to act as a giant, life-saving catcher's mitt. International standards actually mandate something called a RESA, a runway end safety area. Basically, this is a cleared, graded buffer zone extending right past the physical runway. Usually, it's just dirt or grass, completely clear of any obstacles. Its fundamental job? Energy management. If a plane overshoots, the RESA provides a flat, predictable surface that creates rolling resistance. This allows the aircraft to decelerate and sink into the soil without immediately smashing into something catastrophic, like a drainage ditch or a building. But here's the catch. A lot of major airports are built right in the middle of dense cities, or right next to water, and they literally do not have the space for a massive dirt buffer. So when space is super tight, airports install an Engineered Material Arresting System, or EMAS. It utilizes a precast cellular concrete block that is actually surprisingly lightweight and really fragile. And when you put thousands of these together, they act exactly like a runaway truck ramp, but for multi-ton jetliners. You can truly appreciate how thousands of these crushable blocks form a massive, highly customized bed at the very end of the runway, perfectly lined with the pavement. If a plane overruns, its landing gear just rolls straight into this bed. The cellular concrete is specifically engineered to crush under the intense weight of the aircraft. This controlled deformation rapidly and safely absorbs the airplane's kinetic energy, bringing a speeding jetliner to a totally safe, predictable stop. It minimizes damage, and most importantly, it allows the passengers to evacuate safely. It's a real game changer.
And there you have it. You've just mastered the hidden grid of commercial flight. From calculating exactly how thick the invisible air feels, to the secret codes sizing up the wings, the precise rulers measuring the pavement, the split-second physics of a balanced takeoff, right down to the crushable concrete waiting quietly at the runway's edge, you're practically a co-pilot in the secret language of aviation safety now. So, the next time you're hurtling down the tarmac at 150 miles per hour, will you look out the window and feel the weight of all these invisible calculations working flawlessly to keep you safe?